This is the 7th problem on Web Assignment 6 that I'm going to work through here. So number 7, Web Assignment 6. And remember, the red numbers are the ones that are different for you, so just make sure you pay attention to that when you're starting the problem. So mercury with a freezing point of negative 38.8 degrees Celsius is the only metal that is liquid at room temperature. How much energy in joules must be released by mercury if 1.30 milliliters of the metal is cooled from room temperature, which they give to you as 20.0 degrees Celsius to negative 38.8 degrees Celsius, and then frozen to a solid. The density of mercury is given to you at 13.6 grams per centimeter cubed. Its specific heat is 0.140 joules per gram Kelvin, and its heat of fusion is 11.4 joules per gram. So to start this problem, I'm actually going to draw a heating curve for myself so I can mark where I am on the curve to sort of know what steps I'm going to go through and when I need to use Q equals N delta H and when I need to use Q equals MC delta T. So I know that my melting point for this substance is negative 38. So that's my melting point. So if I'm starting at a temperature above that, I'm in the liquid phase, and if I'm starting at a temperature below that, I'm in the solid phase. The problem that I have states that we are starting at 20 degrees Celsius, and it also tells you that mercury is a liquid at room temperature, and it tells you that this is what room temperature is. So I'm starting somewhere up here. Let's just say there. Anywhere above negative 38 is fine, so anywhere along that liquid line, as long as you don't go all the way up into the gas phase. And then the problem states that I'm going to end, alright, so I'm going to cool the mercury until it freezes all the way to a solid. So my end point is here. So I'm going to go along 2 lines. So I'm going to go here and here. So I need to do 2 separate calculations. One will be Q equals MC delta T, and the other one will be when I'm using Q equals N delta H. All right. So for the first part, I'm going to go from 20 degrees Celsius down to the melting point, which is negative 38. So Q equals MC delta T, all right? And then for the second part, I'm going to actually freeze the mercury. So I'm going to use Q equals N delta H. All right, so I need the mass, the specific heat, and the change in temperature for the mercury. I am not given the mass. I'm actually given the density and the volume, so I'm going to have to solve for my mass. I'm going to do that over here. So I know that density is mass divided by volume, and that volume times my density will give me my mass. So the volume I was given in my problem was 1.30 milliliters, and then the density of mercury is 13.6 grams per centimeter cubed, which hopefully you remember from the A half, 1 centimeter cubed is 1 milliliter. So I did that and I got an answer of 17.68 grams. Alright, so back into my heat equation, I'm going to have Q equals 17.68 grams times my specific heat for the mercury, which I was given in the problem. So that was that information at the end. Its specific heat is 0.140. And then something you might notice is that the specific heat for this problem is in joules per gram K. So now, just to call your attention to that, in specific heat, joules per gram degree C is the same thing as joules per gram degree K, because the temperature that you find is a temperature difference. So you're always subtracting the two, which means if you converted each one to Kelvin and then subtracted it, it would be the same difference. So that actually doesn't matter. You can convert them to Kelvin if you don't trust me on that, but it's just subtraction, and so those properties will work out. All right, so then we have the final temperature. So we're going to the freezing point here, which for mercury is negative 38.8 degrees C, and we started at 20 degrees C. That was our initial temperature. All right, so here I get negative 58.8 between those two. All right, and then I will multiply all the way across, and I will be left with a Q of negative 145.54 joules. And this answer should have 3 sig figs. So I'll kind of just mark it there. So my answer there would be to the ones place. All right. Remember, the K cancels out because a change in temperature in Celsius would be the same as it would be in Kelvin. All right. Now I'm along this line here. So now I'm focusing on the phase change part. So since I'm on the melting line, a fancy word for melting is fusion. And so that's where I'll use the delta H fusion. But because I'm going in this direction, I'll change the sign to be negative, because anytime we're going down the heating curve, it's negative, up the heating curve, it's positive. So now for this problem, I would normally use the number of moles of delta H. This problem is slightly different because it gives you the delta H of fusion in joules per gram of mercury, which means you don't actually have to go through the step of converting it to moles because the grams will cancel out with the grams. So all I need to do is actually for this one, this is going to be Q equals M delta H because my delta H is in units of mass. So for mine, I have, again, the 17.68 grams, and that's what I got from the density and the volume, and I'll multiply that by my heat of fusion for mercury, which I make negative, and that's 11.4 joules per gram. All right, and when I do that, I will get negative 201.35, and here my delta H of fusion was 3 sig figs, so this will be 3 sig figs, so this one also goes to the ones place. All right, now for my total Q, I will add both of those together. So I have negative 145 point, sorry, this was 5.4. It doesn't matter, that's gonna kind of go away, but just because I have it carried there. So 0.54 joules, and then I have add to that by negative 201.55 joules, and I will round my final answer to the ones place, so I get negative 347 because that will all get cut off joules. Now there's some kind of like tricks with different problems. Like some of the problems on the key to like one of the sets of practice problems, I would write the amount of heat, the Q would be negative, but then I would just say like this amount of heat is released. So it can be a little bit tricky in the problems on WebAssign to know what they're looking for. In this specific problem, it does want you to keep the negative sign. So be sure you include the negative sign in your final answer there.